Good morning. How's everybody doing today? Cool. My name is Kavya, and today I'm here to talk to you about data race detection, and more specifically, my favorite race detector tool, the Go race detector. Now, like most of you in this room, I think, I write code for a living, and like many of you in this room, I think, that involves reasoning about and thinking and building highly concurrent systems. Actually, just for that warm, fuzzy, we're all in this together feeling, how many people here are intimately familiar with the pains and pleasures of multi-threaded programming? About everybody. Well, that's not surprising. In this day and age, multi-cores power everything from the i5s on your laptop to the Snapdragons or A8s on your cell phones. Everything's multi-core. And we want to write multi-threaded programs to take advantage, to leverage having these multiple cores. Now, obviously, as the number of multi-threaded programs being written has gone up, so too has the number and the frequency of the related bugs, concurrency bugs, like data races and deadlocks. Now, this talk is about the former. It's about data races. And just to make sure we're all on the same page, when I say data race, I mean the situation whereby two threads, which may be user space threads like in Go, or system threads, when they concurrently access a shared memory location, and one of those accesses is a write. So here's an example of a simple, probably what is the most obvious data race. Now, why is this a data race? This is a data race because there is at least one order of execution, at least one ordering of the events, which results in the wrong answer. In this case, for example, if G1's read or G1's write happens before G2's read, we're good, right? We get the right answer, we get the expected answer, which is 1 at the value of count at the end of the program. However, if they race to read and write the count variable, so they both read count at the same time, and then one write happens before the other write, we get the wrong answer, we get 2. And in this case, the accesses are concurrent, and this is a data race. Now, this simple example is going to be a running example for the rest of the talk. Now, what's not a data race? A race condition. A lot of people, it's a common misconception that data races and race conditions are the same thing, but they are not the same thing. Here's an example of not a data race, right? Because of the lock, the accesses to the count variable are synchronized. They will never be concurrent. However, this is a race condition because if your program depends on the value of count, we don't know deterministically ahead of time whether the final value of count is 1 or 2. So this is a race condition. So why do we care about data races? Well, in addition to being relevant, data races are interesting because they're elusive. They are non-deterministic, they're timing dependent, and this means they are hard to write tests for before they happen, and even harder to track down after the fact. And that makes them somewhat fascinating. In addition, they have undefined consequences, right? If your program did something wild with the value of count, and the fact that count had a value of 2 instead of 1 could result in some really crazy things. It's important to point out that data races can also result in unexpected consequences like seg faults or crashes because the compiler assumes race-free programs. And based on that assumption, it makes a number of optimizations. So if your program breaks that rule, if your program is not race-free, then all bets are off. The last feature about data races that make them interesting is specific to a language like Go, and some other languages like Python, which is that it's almost easy to unintentionally and unknowingly introduce data races. The Go map implementation, for example, in the standard lib is not safe for concurrent access. And a lot of new Go programmers just don't know this. So the obvious question at this point is, given we want to write multi-threaded programs, how can we protect our systems from the unknown consequences of these difficult to track down data race bugs in a manner that's reliable and scalable? So the tried and tested method of staring really hard at the code is not an option. It's neither reliable or scalable. At the other extreme, protecting every single memory access with a lock or some sort of sync primitive is not scalable. And this is where data race detectors come in, swoop in, and save the day. These cool tools analyze the given program, either statically, that is based on the source code, or dynamically, as the program is running, and produce a race report that looks like this. This is the Go race detector output run on our example racy count program. It gives us a hell of a lot of information. It tells us the write and read accesses, what lines they occurred at, all sorts of useful things. Now, as the developer, I can just go in and synchronize just that one access that is racy. So are these reliable? Are these tools scalable? These are good questions. The answer is obviously yes, which is why I'm here. But we'll come to the details at the end of the talk. The more interesting question, to me at least, is the how. Is how do these tools detect both memory accesses and synchronization events and detect data races? That is the question I will aim to answer in this talk using the Go race detector as a case study. How many Golang developers do we have in the house? All right, sweet. I can skip over the basics section then. So the Go race detector was introduced in version 1.1, so it's fairly recent. Y'all must be familiar with it. It's available in it ships with Go, so it's available as part of the Go toolchain. You can just do go build install / whatever and pass in the race flag, and you'd get an example output. Now, the Go race detector is a dynamic race detector, and it's based on a C++ library called threadsanitizer that is used widely in Google, if you're familiar with it. And the reason I chose this as my case study is because it's extremely, it's battle-proven. It's found a number of bugs. It's used in industry. It's used on the Go standard library and in Google. And it's open source, which is nice. All right, then. Let's get started. So the rest of this talk is structured as follows. I will first go over the fundamentals required, the prerequisite knowledge to understand the detector. We will then dive into the deep belly of the Go race detector. We'll then take a step back with our understanding and try and evaluate it. And then I'll wrap up and leave time for Q&A. So first things first, and very quickly, since most of you here are familiar with Go, concurrency in Go is available through Go routines, which are user space threads. And you'd use them as you use threads in other languages. Now, the Go memory model is important to understand because it gives us the language guarantees about our program execution. So it says that all the events executed by a Go routine, all the memory access events, are guaranteed to happen in order. But if you have 2 or more Go routines, and they concurrently access some shared piece of data, then their access must be synchronized. Otherwise, all bets are off. So how do you synchronize Go routines? You may use channels. You may use mutexes. And Go also has support for atomics, which is neat. All right. So now that we understand what we need, we have the background knowledge that we need about Go, let's talk about the next core concept, concurrency. Now, if we go back to our data race example, we see that one of the requisites is this concurrent memory access. But how do you determine concurrent memory accesses? With our simple example alone, this is not an easy answer, right? If our program gives us the wrong answer, if it gives us 2, then we know that there must have been a data race. But there are other executions possible. And now you think about a larger program, and this is a difficult question. So in order to detect data races, we need to be able to answer the question, how can we determine concurrent memory accesses? Let's first think about it intuitively. So this is a similar program to our racy count example, minus the Go routines. is the read and write of count, can that ever be concurrent? No, because they're executing in the same Go routine, right? We don't have any Go routines. This is single Go routine, so they cannot be concurrent accesses ever. What about this example? This is, again, similar to our racy count example, in that we spawn 2 Go routines or 2 threads, if you're, that's the way you think about it. Except the access to the if count block is synchronized with a lock. What about in this case? Can a read of count and a write of count from the 2 different Go routines ever be concurrent? No. Again, we know the answer in this case is no, because we have a lock. What the lock essentially does is create a dependency edge of sorts, right? Only one Go routine can acquire a lock at a time. It must release the lock before the next Go routine can acquire it. And since the write and the read are on opposite sides of this edge, we can conclude that they will never be concurrent. That was easy. Now, in the literature, our intuition about concurrency is formalized into the happens before relation. Don't let the name scare you. It's essentially the same idea. Happens before simply gives us a means to order all the events in our system, which may be memory access events, like reads and writes, or synchronization events, like locks and unlocks, across threads or across Go routines. So it allows us to look at all the events across threads, like across the entire program, and order them. Now, happens before has a few rules. In order to say that one event happens before the other, if you've observed their results as such, one of 3 things must be true. Either 1, they happen in the same Go routine, or 2, they're a synchronization pair. And by that I mean they are like a lock-unlock on the same mutex object, or a send-receive on the same channel. Or 3, by transitivity. If we can establish that one event happens before the other, and that event happened before a third, then we can conclude that the first event happened before the third event. If we can establish this, we're good. But if we can't establish that X happens before Y, and Y happens before X, then they're concurrent. Let's apply this and make sure it actually works, because why would you believe me? This is our example with the mutex, with the lock. We know that A happens before B, because same Go routine. By the lock-unlock on the same object principle, we know that B happens before C. And so we can conclude that A happens before D. And this is the same conclusion we came to intuitively, right? We said that the write happens before the read of the next Go routine. What about if we apply this to our racy count example? Well, let's see. There are no edges in this diagram. We know that A happens before B and C happens before D. But what about A and C? What about C and A? There's no edge between them, and so we conclude that they are concurrent. Another useful way to visualize happens before is as a graph, if you think in math. We can establish a happens before relationship if there's a path between them. If not, they are concurrent. Are we good so far? Cool. So now that we know that for data races, we need to determine concurrency, and we're going to determine concurrency by happens before, the next obvious question is, well, how do you implement happens before? And again, for this, we turn to the literature. And the literature says use vector clocks. Are folks here familiar with vector clocks? Okay, so. Okay, so don't let the name scare you. The concept's pretty simple. The idea behind vector clocks is each actor in your system, each Go routine or each thread has its own vector clock. And the vector clock is simply an array of n clocks, where n is the number of threads or coroutines. So we'll work through an example quickly. And each clock corresponds to one coroutine, right? And these aren't clocks in the sense of timestamps. They're logical clocks or scalar clocks. You can think of them as versions. There's certain update rules, and to understand this, let's just walk through an example. So these are the vector clocks of our two coroutines. This uses the count with the lock example. Now, at the beginning of the world, both of them, their vector clocks are initialized to 0. Now, at each event, a coroutine is going to update its index in its vector clock. It's going to increment it by 1. So at the lock, this becomes 1, 0. At the read, this becomes 2, 0. At the write, this becomes 3, 0. And then there's an unlock, and this becomes 4, 0. Now, the unlock is a special event because it's an event that it's a synchronization event. It's going to establish a happens before edge. So at this point, we call this a send event because this is an unlock. Once it unlocks it, it can send the mutex over. And at this point, it sends conceptually. It sends its vector clock over as well. Now, coroutine 2 can receive the mutex. So it sees one event and increments its vector clock by 1. And again, since this is a special synchronization event, a receive synchronization event, it performs this special update. It takes the max of every element in the vector clock and updates its value, its entire vector clock, to that max. So from 0, 1, this becomes 4, 1. Does that make sense? Cool. So vector clocks are supposed to help us determine concurrency. Let's see how that happens. So applied to our program, 0, 0, first event, second event, third event. Fourth event is the unlock, so it's going to send it over. Now at this point, coroutine 2 has an event, and so its vector clock is 4, 1. And its second event. Now, our question is, does A happen before D? And the answer is, if A's vector clock is less than D's vector clock, they happen before each other. A happens before D. Is that true here? Well, 3 is less than 4, 0 is less than 2. So yes, they happen before each other. Now let's apply it to a different example, a more complicated example. Here we've introduced a third coroutine, and we're going to establish a happens before edge between coroutine 1 and 3. So it's going to send something over. With that send, it's going to send its vector clock over too. And our question is does D happen before F? What do you think? No. Right. So we're going to compare their vector clocks. And we see that every element in D is not less than every element in F. So they don't happen before each other. What about F happens before D? For the same reason, F does not happen before D. And since they don't happen before each other, this is a concurrent access. So at this point, you're probably thinking, well, cool, Kavya. Now I know all about happens before and vector clocks, but why did we just go back to grad school? And the answer is, because this is what the Go race detector does. It determines if two memory accesses are concurrent by establishing this happens before relationship. And to do that, it uses vector clocks. This method of race detection is called pure happens before detection. There are other types of detection, but this is the one we'll talk about today. All right, everybody with me so far? Cool. It is now time to dive into the deep, deep belly of the Go race detector and look at how it's implemented. So in order to implement happens before using vector clocks, what would the Go race detector need to do? Well, let's see. It will have to create vector clocks for Go routines at Go routine creation. It will then have to update these vector clocks at each memory access and synchronization event. And then at each memory access event, it has to compare these vector clocks to decide if there's a data race. Now, if you stare really hard at these bullet points, and maybe the coloring will give you a hint, you will see that we can essentially tease out two subproblems, a problem of event generation and a problem of event consumption. And we're going to make it the program's responsibility to handle the event generation, in that every time the program performs a Go routine creation or a memory access, it's going to report it. And the race detector is simply going to consume these events and take care of updating its state. It's going to create the vector clocks. It's going to update the vector clocks. It's going to take care of all of that. At a high level, this is how the Go race detector is implemented. It's implemented conceptually as a state machine, whereby the program, as it's running, generates events. And the race detector keeps program state, vector clocks, et cetera, and it updates them based on the events it receives. But problem, does this mean that we have to modify our programs? So at every memory access, at every synchronization, every Go routine creation, do we have to call out to the race detector? Do we have to modify our programs? Well, no. We just saw that we can take our program and run the race detector on it. So what's going on? To answer that question, let's look at the source. So this is our racy count program, compiled without race detection enabled. This is what the assembly for the increment count function alone looks like. And this is uninteresting. This looks pretty standard. The function's defined. Now, if we compile the program with race detection enabled, what does the output of that look like? Well, for one, it looks longer. But there's something else. There are a number of extra calls inserted. There is a race func enter. There's a race read, a race write. What's happened is that the Go compiler, the GC compiler, has essentially transformed our program to look like this. Whoops. To look like this, right? It's inserted the calls out to the race detector for us. Now, the way the compiler does this is pretty standard, so I'm not going to go over the details. The idea is that if race detection is enabled, it adds an extra instrumentation pass over the IR. So it essentially modifies the code tree generated. Well, this is awesome. It means that we don't have to modify our programs to track memory accesses. Well, what about synchronization events and Go routine creation? For that, let's look at the source of the Go standard library. This is mutex.go. This gives us the mutex sync primitive. And we see that there is an if race-enabled block, which essentially calls out to a race detector function, race acquire. Similarly, Go routines are created in proc.go, right? The new proc1 function is what's responsible for creating a new Go routine from the Go standard library. And we see the same if race-enabled block with a function call out to the Go race detector. Cool. So what did these functions do? For that, let's go to their source and see what's going on. Well, ignore the fact that it's an assembly file. We can talk about it later. But what we notice is that there's a call to tsan read. This is a call to the threadsanitizer library, the C++ race detection library that we talked about. The Go erase detector isn't just based on TSAN, it's literally built on TSAN. It calls into TSAN. So at this point, we know two things. We know that one, the program can generate these events for us thanks to compiler instrumentation and the Go standard lib. And we know that the erase detector, the magic sauce that takes care of all the state, is TSAN. So how does TSAN work? Well, TSAN implements the happens before detection. So what does it need to do? If we go back to our checklist, we see that it has to do something with vector clocks, right? And to do this, it uses something called thread state. It needs to compute these happen before edges. And to do that, it uses those two data structures. And finally, it needs to compare vector clocks to detect data races. Rather than talking about the details, let's just look at an example. So this is our program, and we'll see what TSAN does at each step. So the first call to spawn a Go routine, go increment count, results in a call out to TSAN, as we saw. And at this point, TSAN creates this thread state. Now, thread state simply contains the vector clock for that Go routine. And it returns it to the program so it can be stored on the Go routine. All right, so check. We have a vector clock for our Go routine. Now we're going to perform a read. We're going to check count equal to 0. Now at this point, TSAN has to do two things. It has to check if there's a data race with the previous access. And if there isn't, it has to store information about this access for future detections. Let's look at 2 first. To do this, TSAN uses something called shadow state. It essentially creates a shadow word to track each memory access. And this stores information about the access, like the thread ID, the clock, the position, like where the access occurred, and whether the access was a read or a write. Now, the shadow state is directly mapped. The details don't matter. Now, TSAN performs 2 optimizations to the shadow state. The first is, rather than storing 1 per memory access, because that would just consume a lot of memory, it stores a fixed number of shadow cells. In the current implementation, it's 4, for a region of memory. Let's just see how that works. So if there is a read to the first 2 bytes of an application's word, this is the shadow word created. Now, if another Go routine comes along and writes to the last 4 bytes, this is the next shadow word created. Does this make sense? Cool. The second optimization is that TSAN does not store the entire vector clock. It only stores the scalar clock, which is the accessor's index in its vector clock. Now, these 2 optimizations may seem surprising. Doesn't it cause a loss in precision? It turns out to not matter, as we will see. So going back to our program. So the read of count translates to the creation of this shadow word, right? We have the thread ID. We have its clock, which is 0. We have the region red, and we have a 0 because it was a read. Now at the count, there is another shadow word created that looks like this. And here's where it gets interesting. G2 comes along, and G2 performs a read. And this is what its shadow word looks like, right? There's G2, 0, 0, 8, and 0. At this point, TSAN's going to check if there's a race. Let's see how that's done. Okay. The algorithm at this point is beautifully simple. All you have to do is check the accessor's vector clock. That is the full vector clock, and the new shadow word with the existing shadow word. Let's see how this works. So what exactly are we checking for? One, do the access locations overlap, right? Are they reading a shared, are they accessing a shared memory location? Yes, they are. Are any of these accesses a write? Why, yes, they are. Are the TIDs different? Are these two different Go routines? Why, yes, they are. And lastly, can we establish a happens before edge between them? Well, let's see. We're going to use vector clocks, right? That's why we learned about them. So we're going to take G2's full vector clock and compare it to the existing shadow words clock. In order to decide that the read happened before the write, we need the shadow words vector clock to be less than the G2's vector clock, right? Is that true in this case? Well, no, it's not. Well, 4 red check marks, what could that possibly mean? It's a race. So at this point, we've seen how TSAN implements race detection. This was the simplest example. There's obviously a lot more. TSAN's this hella huge C++ library, but a few important notes. First, TSAN obviously must track synchronization events as well, right? Now, these events are important because they establish the happens before edges. And in order to facilitate that transfer, that exchange of vector clocks, TSAN uses like a sync var, which is another data structure. But the interesting thing about this data structure is it stores a vector clock as well. So when a sender and receiver manipulate it, the vector clock is effectively transferred over. The other point to note is that TSAN tracks file descriptor, memory allocators, and all of that. The goal of this being that it is able to recognize implicitly synchronized events too. So not just explicitly by a lock or channel, but implicit synchronizations that may happen through file descriptors. TSAN recognizes that. The goal of this is so it doesn't report false positives. Speaking of false positives, let's quickly answer our remaining 2 questions. We know how the how works, but we still want to know, is it reliable? Is the Go race detector via TSAN scalable? Well, first question. Well, TSAN, or the Go race detector, does not report false positives. So if it reports a race, there is a data race. There is some ordering of events in your program that would result in a data race. But just because it reports a data race, it doesn't mean that it's dangerous, right? There is such a thing as benign data races, and that's up to you as the programmer to decide the consequences of the data race. It can miss races, though, and this is important. This is a property of dynamic race detectors that they depend on the particular execution of the program that you run them on, right? So for example, if we ran our example program an enough number of times, there would be at least one execution where there wouldn't be a data race. And in that case, the race detector wouldn't report a race. So it depends on the actual events that occur. And is it reliable? Well, yes, it's battle proven. Like we said, Google, LLVM, there are a number of users out there. Our second question, is it scalable? Not really. This is the program slowdown, the execution time, and that is the memory usage overhead of using the Go race detector. But is it scalable with respect to finding data races? Well, it's more scalable than staring at your giant code base. And it's certainly more scalable with respect to your program's performance than locking everything and shipping that to production. The recommended use of the Go race detector is in your testing environment or on your staging environment or even like a production cannery box. And it works well for those purposes. All right, that brings us to the end of the talk. Thank you all for coming. As you leave today, I hope you walk away with an appreciation for the fascinating nature of the race detection, the data race detection problem. And I hope you've learned about happens before, and happens before using vector clocks. And I hope you've learned about the Go race detector and how that works by compiler instrumentation and this hella cool TSAN runtime library. Thank you. We have about 5 minutes for questions. Yes?
Can you explain a little bit, like, in more details how this, like, TSAN works with multiple variables, like, like those, like, remaining, like, memory addresses?
Yes.
Pass them to TSAN. Like, you have to, like, have the vector per, like, memory address, right?
Right. So I rushed over the optimization sections. We can go back to that. Yeah, that's a great question. So this is the simple scheme, right? Where you store one shadow word per memory location, per access. And you can see how that would work. But the optimization that TSAN performs is for an application, for 8 bytes of the application. So for a word in a 64-bit. But for an entire word, it's tracked. Only 4 accesses to that entire region are tracked, okay? And you might think if you only keep the last 4 accesses and evict accesses, this might affect precision, and that's true, right? But the race detector doesn't claim to not report, it doesn't claim to be like foolproof, right? Yeah, so that's okay. Now let's see how this actually works. So say that there's an access, a read access to those 2 bytes. This is the shadow word created. And we know that it's those 2 bytes that were accessed because of the position and the offset, which says 0, 2. Now, if there's another access to this region of memory, like a write of the last 4 bytes, that index is 4, 8. So we know that it was to a different region, yeah. If there was another region, like if there was another block, that would be tracked by another set of 4. Yes, that's right. And the shadow state is stored in, whoops. Yeah, no, it's not 4 ever. It's 4 per 8 bytes of the application. Thank you. Thanks. Thanks. Yeah.
What do you think of the prospects of static data race analysis in Go or other languages?
That's a good question. Let me pull up my.
That's a little outside the scope, but when you talk about the 5x, 10x memory usage.
Yes. Yeah. So an alternative to dynamic race detection is static race detection, right? So in static race detection, the race detector analyzes the program source. And the advantage of this is that only a single pass of the program is required. And that single pass should report all races. And so it ends up being more effective in that sense. But the problem with it is that you have to change your source code. For static race detection, you'd have to add these annotations to call out to the race detector. And that's obviously, for larger code bases, that's not something that they want to do. With respect to the potential for it in a language like Go, well, I don't know of a good reason why it hasn't been implemented. I think the reason that the Go race detector is what it is because Go was created at Google, and TSAN was widely used at Google. So at the time it came down to choosing a race detector, I believe that was like one of the leading factors in the decision.
I think like for static race detection, you have to like hold different counter crust after building the language semantics.
Mm-hmm. Any other questions? Yes. Yes, so TSAN requires like help from the compiler to run, right? The GC compiler in Go, so Go has two compilers, the GC compiler and the GCC Go compiler. It's not supported by GCC Go, but the GC compiler supports this. In addition, you can also use TSAN with the later versions of, or not late anymore, but with certain versions of LLVM, LLVM's Clang, and with GCC. And that you would use that for race detection in C, C++.
You briefly mentioned that TSAN supports the synchronization for like file descriptors and network things.
Yes.
And does Go instrument this as well?
Yes.
Oh, nice.
Yeah. Yeah, it's pretty cool. The other neat thing about TSAN is that it allows, it recognizes your custom synchronization primitive via dynamic annotations. So if you created your own class or like your own object and you wanted that to behave like a synchronization primitive, in that you wanted that to establish these happens before edges and not report data races on that, you can arrange for TSAN to do that by dynamic annotations, which is pretty neat.
Like insert this like Go calls on like runtime dot whatever like.
Yeah, you probably could. Yeah.
Like if race enabled, same thing.
Yeah, I think so. Yeah. Mhm.
So why does it need to track synchronization operations? Like, I think I understand that in order to synchronize the vector clock, but it seems like you could, if things are properly synchronized, and it's like tracing the execution of the program, you would never have a collision anyway. So, like, what role does the tracking of synchronization operations play in TSAN?
So this comes back to like happens before, right? In order to get a partial ordering over all the events across Go routines, you must be able to recognize those edges because that's what establishes the ordering.
What you're talking is like the read and write is an internal events, and the mutex is an external event. That's why it's different semantics. And when you issue the log as an external event, at this point like TSAN logs internally and synchronizes vector flow.
Right. So it's just basically the vector clock.
Yes, yeah, exactly. It's to facilitate that exchange of vector clocks because what needs to happen is when there's a synchronization event, TSAN needs to update the thread states, right? To the vector clocks stored in the thread states to reflect the fact that there was a synchronization event.
Otherwise, it couldn't guarantee that one event happened before the other.
Yes.
Like, as far as memory synchronization.
Yep. Yeah.
How does this compare to the Intel System Studio?
Oh, I have not because it's proprietary. You can't get access to it, or I would have used it.
Yeah, so some of the tools, they inject artificial delays and those kind of things.
I see.
Can you repeat the question? Sorry.
Sorry, I should be doing this. The question was, how does this compare to the Intel? Intel has a race detector. What is it called?
System Studio.
It's called System Studio or something like that. But the question was, how does the Go race detector compare to the Intel race detector? And I believe it does something by injecting.
Yeah, it injects artificial delays in the execution. You don't have to instrument your code.
I see.
For it to detect.
Okay, cool. Nice. Cool. All right, thank you. I believe lunch is outside.